So we're getting into stresses and beams. But the idea is, for example, let's say you have this beam that's connected to the ground by a hinge and a roller at the center, and let's say it has some mass, 50 kilograms, and let's say that there's a downward force of 2,000 newtons at the end. And let's say we know something about the cross section, we know the dimensions. What are the stresses in the beam? Let's say at this point A here, okay. Well, notice that where I drew that line A, that actually represents a finite area. And so an area is made up of infinitely many points. And so even specifying that we want to calculate the stresses at this like level along the beam left and right, we have to represent the stresses along the cross section in the cross section as some kinds of functions of like the y and z components. But that's what we're trying to get to, basically. Like you have, so if you have a big structure, you know, calculate the stresses so you can figure out which of these members is likely to break. You have to beef up the geometry of some of these members, that kind of thing. And in order to do that, there are a couple of things that we're going to have to talk about first. We're going to have to talk about internal loads and beams. And then we're going to have to, okay, so, but you all did distributed loads and statics, right? Yeah. So this is for point and distributed loads. You can think of those as the internal tension, T, the shear force, capital V, the bending moment, M, the internal torque that I'll do as like a fancy T, and then after we've talked about internal loads, we'll talk about how to use those internal loads to calculate the stress tensor due to that internal tension, the stress tensor due to the internal shear force, the stress tensor due to the internal bending moment, and the stress tensor due to the internal torque. And then once we have all these, the total stress tensor is just going to be the sum of these, of all of these. Whoops. So the first thing we have to talk about is internal loads and beams. And the idea of internal loads and beams, I can't remember if I drew this picture earlier, but imagine taking your two hands and like bending a long, slender, stick, piece of wood. If you look at a free body diagram of that stick, you see a force from the fingers here, a force from the thumb, a force from the thumb, a force from the fingers. And so if all you had to look at, all you had to go on was the free body diagram, you would think like, well, the most likely places for this to break would be at where one of those external loads is applied. But you know from experience that that's actually not, none of those four places are where the stick is going to break. The stick is actually going to break somewhere between the two thumbs. Okay. So the fracture doesn't happen at the external loads. And so the question is kind of like, is there some way to use forces to measure where this thing is likely to break? And the way it works is at every horizontal location, material on the right side is applying loads to material on the left side. Vice versa means the same thing. We can look at either one of those sides. But the key thing isn't the force that's externally being applied. The key thing is the force that's required for one point to have applied by the surrounding materials in order to maintain static equilibrium. Okay, so if these, if the loads that are required for static equilibrium get too big, then the material on one side, lets go of the material it's connected to. And the stick breaks. So in other words, for figuring out when something's going to break, it's not really important to figure out what the external loads are, where the external loads are big. what's really important is figuring out what the loads are that the material has to apply to the adjacent material. When that gets too big, that's when the two pieces of material separate from each other. And that's so this is this is the internal loads. Those loads that one side of the stick has to apply to the other side of the stick. Okay, so let me show you, let's just kind of reason our way through this, where we had like a roller somewhere, we had some kind of force applied, and we wanted to analyze what the internal loads were at this point here. Okay, so 500 Newton meters. What are the loads applied to the left piece left of that red line by the material on the right? That's what we're getting at. And remember, the way that we did that is we assumed that this is a fixed joint between those two pieces of material, and a fixed joint is capable of applying a force along every axis and a couple about every axis. Okay, so let's say we have, so I'll do that same thing. I'll just give some dimensions. So let's say we have a roller at the midpoint. The line where we want to calculate the internal loads is here. Let's say that's 0.25 meters. It's another 0.25 meters to the roller. And then it's half a meter to the end. And at the end, there's 1,000 Newton force acting down and a torque of 500 Newton meters twisting it. Anyone have a sense for like what a Newton meter is, like how strong a torque that is? Anyone have a ballpark figure for what kind of torque you could apply with like a screwdriver with all your might? Yeah, right. That's what I mean. Like, yeah, probably people have foot pounds and stuff. Yeah. Well, I'd say this is the thing that I think of to remind myself what that means. With a screwdriver, I can apply a torque as hard as I can with one hand of somewhere right around 10 Newton meters. Okay, but I'm probably stronger than you guys. Okay, so the first thing we have to do is calculate the external loads. So first I'm going to do a free body diagram of the whole beam. There is an unknown reaction force from the pin. I'll call that RA. At the roller, at the midpoint, there's an upward normal force. Call that N. And then we have these other two external forces, the 1,000 and then the 500 Newton meters. And now this is a rigid body problem to calculate those external loads. I'm going to put the about point here. And a lot of you guys have seen this in dynamics, or, Charles has seen it in statics, but for rigid bodies, you can always write out this table with a row vector, a force vector, and a moment vector for every load. For me, it helps me just sort of keep track of what's going on. What we're going to see is that with this kind of problem with a horizontal beam, it's pretty easy to just do it in your head by thinking about, okay, that force causes either a clockwise or a counterclockwise rotation around that point. But I'm going to start out by doing it in this sort of formal, full way. So first, that force RA. RA acts at the about point, so the row vector is 0. The force vector is RAX, RAY, 0. And the cross product is the 0 vector. Then that force N, the vector from the about point to where N is applied is positive 0.5, 0, 0. I'm using X horizontal, Y vertical, and that means Z is coming out towards us. So the force vector is 0, N, 0. And the cross product is 0, 0, positive 0.5 N. And then these other two, I guess I'll do the 1,000 Newton force first. The row vector for that is 1, 0, 0. The force vector is 0, negative 1,000, 0. Cross product of those two vectors is 0, 0, negative 1,000. And then the last thing is that couple. For couples, the about point doesn't matter. The net force is 0, so these go away. Yeah. Did I say 1,000? Negative 1,000. And okay, so what's the direction of that couple? Well, if you have it drawn like this, that just says that it's in the positive X direction. So this is going to be 500, 0, 0. And now Newton's second law, you can just add up all the forces in the force column. We don't have any in the Z direction. See, that's 0, that's 0, that's 0. So the only places where anything's going to happen are the X and Y axes. So we have RAX, RAY, plus 0N, plus 0, negative 1,000 is equal to zeros. Ooh, we're missing something important. If this was all the loads that were happening, there's no way this could be an equilibrium, because if you're applying a torque of 500 Newton meters and there's nothing to resist that motion, it's just going to spin. So we also have to consider a reaction torque. I'll call it fancy TR. It will end up being the other way, but I'm just going to put it in the positive X direction and let the signs work out on its own. Okay, so this is TR. Again, this is a couple, so we don't care about that stuff. And we just have TR, 0, 0. What's applying that couple? Well, the idea is if you have a hinge here, imagine like a physical pin going through that member, that would keep the member from turning this way. Okay. Okay, so that didn't affect Newton's second law, but it will affect the moment equation. So rotational Newton's second law, I'm going to do it in the x direction and the y direction. So the x direction says 500 plus TR is equal to 0. So in other words, TR is equal to negative 500 Newton meters. And then the moment equation in the z direction says 0.5 n minus 1,000 is equal to 0. And so n has to be equal to positive 2,000. And now we can plug that into Newton's second law, and we get that this vector RA has 0 for an x component and negative 1,000 for a y component. Okay. So that's sort of a interesting thing. In order to have rotational equilibrium met, even though, like in a sense, these are resisting a downward force, you might think that they'd both be applying upward forces. That's actually going to, the way it's going to have to work is that that pin is going to have to pull down on this member to keep it from rotating. Okay, so now we have the external loads. Now we're going to calculate the internal loads. So free body diagram of the left, like everything left of the red line. So that's the piece. And then there's all this stuff that's not included in our free body. And that includes the downward force, that couple. But what is included is a downward force of 1,000. That's the RA that we calculated. I'm just gonna write that as a downward force of 1,000. And a couple this way of 500 Newton meters. And then the internal loads, which you can think of as, since the connection between what we're including and the light blue part that we're excluding, we can think of as a fixed joint. You can treat this as a force vector. For now, I'm going to call that R. So that's an X and a Y component. And then a couple, I'll call that M. And then a torque about the x-axis that I'll call fancy T. Yeah, it's just the different axes. So this is about the z-axis, and this is about the x-axis. I could have just written that as an M vector that just has couples for every component. We're never going to deal with couples in these problems about the y-axis. So I'm just going to call them separate things for x and y, or x and z, sorry. Sure. Yep. Okay, so now let's go to Newton's second law. You could write out the row vector, the force vector, and the moment. I'm going to make this the about point, and that's where I'm always going to do the about point and these kind of things. So Newton's second law says we have a downward force of 1,000. So 0, negative 1,000. And then we have Rx and Ry. Nothing else is a force. The other stuff was couples. So this is equal to 0. And so that internal load R is equal to 0, positive 1,000. And then we'll add up all the moments in the z direction. I don't know why I'm doing z first, but it doesn't matter. They're separate. They're uncoupled. So in the z direction, does that 1,000 Newton force apply any moment? Nope, not with that about point. It goes right through the about point. Does the x component of r? Well, there is none. It wouldn't anyways, because its line of action goes right through that about point. The y component does. Okay, so we have a force of 1,000 newtons times a moment arm of 0.25. And would that upward 1,000 Newton force make it rotate clockwise or counterclockwise around the about point? Counterclockwise, so that's going to be a positive moment of, 0.25 times 1,000. And then the only other thing that produces a moment about the z-axis is m. So we have plus m. That adds up to 0. So that internal bending moment is equal to negative 250. And then the last thing is the x component of the moment equation. The only things producing moments about the x-axis are couples. So we have the negative 500 and the positive t. They add up to 0. And so that internal torque is positive 500 Newton meters. Okay, so that's the idea, except we did all this work and just calculated the internal loads at this point, okay? And normally you want to know, you'd want to look at this and calculate where it's most likely to break. What we did could help us calculate whether it's likely to break at that point, but we don't know how it's going to change as you go across. So the first thing that we'd like to be able to do is calculate those internal loads as a function of x as you move along the beam, okay? The second problem is notice that the way we calculated those internal loads, like we just used vector components for the couples and the forces, and we got these internal loads like we wanted. But think about what would happen if we arbitrarily chose to isolate the left part and calculate the loads applied to the left by the right. We could have just as easily isolated the right and calculated the loads applied by the left. Would we have gotten the same things if we'd done that? How would it change? just different signs. Yep, because of Newton's third law. Okay, and so we're going to do the two next steps are so the first one is we're going to introduce a new sign convention for these internal loads. And what this sign convention is going to do is it's going to make it so that no matter which part of the beam we isolate, we get the same answers for what's happening at a certain point. That's preferable, you know. So that's to deal with getting different answers in the different directions. And then the second thing we want to do is the function thing. We want to calculate these internal loads as mathematical functions of x. So that then we can like look at this function or graph it out or whatever and say, okay, this point right here is where we want to check and see if it's going to break. If it's good there, then we're good over the whole thing, you know. And the example that we did was you have a beam with a pin joint here. This way, there's a roller at the midpoint. This distance is 0.5 meters. This has been acting all funny recently. Okay, 0.5 meters, and then this other half is 0.5 meters. And there's a 1,000 Newton load of downward force here. And then there's an external torque of 500 Newton meters here. And last time what we did was we calculated the internal loads at that blue line. So last time we calculated the internal loads at this location. Using a coordinate system sign convention. And what I mean by that is that whenever we calculated those internal loads, we thought about the point of contact as a fixed joint, and the fixed joint we represented as providing an x component of force, a y component of force, a z component of couple, and a x component of couple, okay, in this coordinate system. So we're using this coordinate system. And we were able to do it. Does anyone remember what the problem is with that? With using that sign convention? So the problem with using a coordinate system sign convention is if we happen to isolate the other half of the beam to calculate those internal loads, so if we isolated the other side of the desired location, all the internal loads would be opposite signs. So the calculated internal loads would switch signs. And what we want is a single set of internal loads that we can, no matter how we calculate it, we're just going to say at this location, the internal loads are this. So we're going to come up with this new sign convention that doesn't just depend on the coordinate system, that we can use from either side, and it's going to give us the same answers. Okay. So the next two steps are these. First, we're going to introduce a new sign convention. That doesn't have, so without that Newton's third law problem, the thing above, the reason that you switch the signs if you switch which side you're isolating. And that's going to look like this. So when you think about isolating a point on the beam, you can think about it as being an infinitesimal sliver. Okay, that is a finite sliver, but imagine it being infinitesimally thin. Then a positive value of what we were just calling the x component of the force before. On this side would be this way, and this side would be this way, and we'll just call that capital T for tension. Okay. So now if we isolated the beam the way, so if we isolate the beam the way we did before, this half, then a positive value of T is that way. If we went from the other side and isolated that, a positive value of T would be this way. And that way, no matter which way you go, you get the same answers. How many other loads, how many internal loads did we have to deal with, remember? 4, yep. So we had to deal with the x component of the force, the y component of the force, the x component of the couple, and the z component of the couple. So I'm just going to go through all 4 of those. The other force, so this is tension, compression. If it's negative, it's compression. So tension would be positive, compression would be negative. Then the y component of the force, if you're dealing with this side, it's this way. If you're dealing with this side, it's this way. This is called capital V. I'm not sure what that stands for. And this is called the shear force. And then the 2 couple components. Nope, doesn't mean anything. Right, it doesn't really have any different, like, intuitive meaning. And then about the z-axis, there's a couple that way, or if you're on the other side this way, those are capital M. That's called the bending moment. And again, the sign doesn't really mean anything qualitative. And then the last one is the torque about the x-axis. So that's a couple this way or a couple this way, depending on which face you're on. And I'm going to represent this, since this is called the torque, I'm going to call it capital T, but I'm going to do it all fancy like. So this is the torque. Okay, so let me do that same problem over again, this time with that new sign convention. So we're not going to ever deal with ones that are going into or out of the page. And really the main reason that we're not is because we don't currently, like in this class, we're not going to have a way to calculate the stresses for things that are bending in bending around more than one axis. Okay, so we could calculate those internal loads. That wouldn't be hard to modify this to do that, but we still wouldn't be able to calculate the stresses. So, and then that brings up another point. Like, so what if this is the beam and it's fixed to the wall, and you're applying, the only force you're applying is like this to it? Well, just think of it like that, and then you're fine. You know, we're going to have to do that a lot with these kind of things, you know, but that's always implied. The coordinate system just relates to the kind of the axis that the load is happening on, not really to up or down, you know. Okay, so back to the example from last time. Oh, no, I got carried away. Here, put this aside for later. Yeah, I need a step 2. And then step 2, we are going to expand, so we're not just calculating it at a single point along the beam, but we're calculating these internal loads as functions of x as you go along the length of the beam. So calculate the internal loads for the entire length of the beam as functions of x. Okay, so now back to the example from last time. We already calculated all the external loads. And so I'm going to do a free body diagram of the left half again, or not the left half, the left side of that place where we want to find the internal loads. So I'm including the stuff in black, and I'm skipping all the stuff, the dotted line stuff. So that means we're not considering the downward 1,000 Newton force. We're not considering the couple. We did use those to figure out the external loads on the left side, and those are a downward force of 1,000 newtons and a couple with your thumb in the direction of the negative x axis of 500 Newton meters. I'll just put the units on here so we keep the couple and the force straight. Okay, and now what we did before was we called it a force vector, and we called it a couple component in this direction and in this direction. Now I'm going to use the sign convention that I just gave you for number 1. So we have a tension T, a shear force, and now our default direction is down, V, although it still has the same information in it that the y component of a force vector would. V, yep. Then the couple, that's the component of the moment about the z-axis. We call that capital M. And then finally, the internal torque, fancy T. That's right. I mean, you can, it's just a variable, I guess, but a lot of times for an external torque, I'll use the variable TR for like reaction torque. I guess it's not like a crucial thing, but yes, you always do use it for internal when you're doing internal torques. Okay, and then Newton's second law. So we have no x forces. We have this downward 1,000 Newton force, so 0, negative 1,000. Yeah. Mm-hmm. Yes, exactly. So this is, so the infinitesimal piece is this. So the blue represents the line you're looking at. The red box is infinitesimally far to the left and to the right of the line that you care about. And so we're doing our cut from all the way at this end to the far end of that infinitesimal piece. So what we're isolating is, so the piece that we're isolating is this with our desired line there, okay? So we're not dealing with any of the internal loads on the left side of that isolated sliver. We're only dealing with the loads acting on the right side of that sliver. So we're only using the sign convention of the right side. Yeah. And then we go all the way from the far end to the point that we care about. So these are still the external loads. The only internal loads are on the right side. Okay, so let's just keep going through these forces. We have the 1,000 going down. We have the tension going to the right, so the positive x direction, so that's T0. The V is in the negative y direction, so now writing this in vector form, that's 0, negative V. That can be a little confusing. But if you always just think about the arrows here, so whenever you're looking at the free body diagram, you have an arrow that represents a unit vector, and you're multiplying it by a number represented by the variable. Okay, so what's a unit vector in the direction of this downward force? 0, negative 1, multiply that by V, and you get this vector 0, negative V. Okay. And that's all the forces. So set that equal to zeros. And you get that there's no internal tension. And the internal shear force at that point is negative 1,000 newtons. And now we'll do the moments about the, let's do the z-axis first. So we're using the rotational Newton's second law about the z-axis. And our about point is going to be this. It always is, all the way at the left end. It doesn't have to be, you know, from statics it could be any point, but this is just going to make the math a little simpler. Okay, so what produces moments about the z-axis with this as the about point. Not this one. That's in the negative x direction, right? That doesn't have any z component. Not this one, because it acts through the about point. Okay. What about the tension T? No, that the line of action goes through that point. What about torque T? No, that's x direction. M does, though. That's a couple about z. And what about V? It does. And so let's see. So the only ones we have are M. So adding on that couple M. And then what's the moment applied by this V? Okay, so we definitely have that couple M. That just gets added on. That doesn't depend on the about point. And then we have, and what's the sign of that moment? That's V times 0.25. Negative, because it would cause a clockwise rotation. So that's minus 0.25 V. Okay, so we got this. Then there's nothing else that produces moments about the z-axis. So that's equal to 0. And so this says that M is equal to 0.25 V. But we already know V from the step before. So that's, 0.25 times negative 1,000. And so M is equal to negative 250. And this is Newton meters. And then the last one is we have to do the x component of the moment equation. These x ones, since we're assuming that this beam has no thickness and we're going to keep doing that for these calculations, all we're going to ever be dealing with are these couples along the x direction. So all we have is a 500 Newton meter couple in the negative x direction and a positive t couple in the x direction. Okay, those are the only things that produce moments about the x-axis. So we have negative, what was it, 500? Plus fancy t is equal to 0. So fancy t, that internal torque, is equal to 500 Newton meters. And what changed this time is now, if instead of isolating this piece, we isolated the piece in the dotted blue and calculated the internal loads with all of these, using the sign convention that I gave you, so all these would be opposite, we get the same values for those internal loads that we just did. There wouldn't be the Newton's third law problem of everything being reversed. Okay. So what's the next step? So now we want to figure it out, not for just that single point, but now what we want to do basically is we want to isolate a piece like this that doesn't have a length of 0.25 meters. It has some arbitrary length x, yep. And we're going to calculate all these in terms of x. And once we have that, in this case, that'll be a function that represents the whole beam. We'll see that you have to do it as a piecewise function in most cases, but this one will work as just a single function. Okay, so now we're going to isolate a piece on the left side of the beam with length x. So I can draw it the same way that I drew this one. And we're still ignoring all this stuff on the right side. We have a downward force over here of 1,000. A couple of 500 this way. And then we have the internal loads, T, V, M, and fancy T. And this time, this length here isn't a quarter, it's X. Okay, but you can imagine, I mean, nothing conceptually is going to change about how we approach this. It's just, I mean, where was the only place in our last calculation where that length came into it? Yeah, and calculating the moment M. And so this time, when we sum up the moments about the z-axis, we're going to have this M, and we're going to have this B times X, you know. So what we're going to have to do is a piecewise function where for all x's between 0 and 0.5, this free body diagram represents the body. Okay. Then for all pieces from x equals 0.5 to 1, our free body diagram is going to have to include that piece. Okay. So let's see. So let me write this down. This free body diagram represents everything from, okay, so at one extreme is this, where we're leaving all this off. And you have this downward force, this couple, these internal loads, okay? But we're leaving off this, this, and this. Are you with me on what that's supposed to look like? 2, at the other extreme, you have this downward force, this couple, these internal loads, and then we're just missing getting to the next one, and we're still ignoring these. Okay. So this represents like, this one represents x equals 0.00001, you know what I mean? And this one represents x equals 0.49999. Okay. Okay, so from this free body diagram, let's do Newton's second law. For the forces, there's the downward 1,000 Newton. And I guess I didn't explicitly say this, but like, even though obviously the lengths of those look very different, look at what loads are applied, and this sort of general description of what's going on applies to this and to this. The only difference is that X value. Okay, are you with me on that? All right. So the forces, we have a 0, negative 1,000. And then we have a T0. And then we have a 0, negative V. And those add up to zeros. So from those two equations, you get that T is equal to 0 and V is equal to negative 1,000. And now we'll add up the moments about the Z-axis. Our about point is where it always is, right at the end. That 1,000 doesn't produce one, the 500 doesn't. The only things that do are the M and the V. And so we have plus M minus Vx is equal to 0. We know what V is, so this tells us that M is equal to negative 1,000 X. Because M is equal to Vx and V is negative 1,000. And then we'll add it up for the X component. You have a 500 Newton meter couple in the negative X, well, in the X direction, negative 500. And then you have fancy T. So negative 500 plus T is equal to 0. And so T is equal to 500. Okay, so where are these functions valid? We came up with these functions. I mean, only one of them looks like a function of X. But what we figured out is none of the other ones change as X changes. Where are these functions valid, though? For what X values? So these are all valid on the interval X between, so this, which is basically 0, just a little bit to the right of 0, and this, which is basically 0.5, just a little bit to the left of 0.5. So these functions are valid for X between 0 and 0.5, not including the endpoints. And so now based on this, so now we've done a calculation that represents all of the X values, all of the points along the beam until right before you get to that roller. T, V, and fancy T, they don't change, so we don't have to worry if the different points aren't any different. This one does change though as X changes. So based on this bending moment, where would you be most concerned about this beam breaking? Would it be close to the left end of the beam or close to the roller? Yeah, it's close to the roller because you go from an M value of 0 to an M value of absolute value of 500. Okay, so if this is going to break anywhere, over the region that we've looked at so far. It's going to be as you get close to the roller. We need a new free body diagram for the second half. Okay, so this time a representative free body diagram has to go past the roller. Okay, we're still skipping some of the beam. So this time the external loads we have are the 1,000 down, the 500 to the left, that's the torque, the roller at the midpoint, and that has a value of 2,000, and then the internal loads, T, V, M, and fancy T. And now we're going to call this whole distance X. Okay. And this represents everything. So this free body diagram represents everything from this where the roller's right there. We have the force, the torque, and then the internal loads. And for this one, X is equal to 0.50001, something like that. 2, one that covers almost the whole length, where we're only excluding just a tiny little sliver. But it's the tiny little sliver that has these external loads on it. We still have the force from the roller here. We still have the internal loads. And this one is what's X equal to in this picture? Yeah, exactly. It's just right up until you get to that end. Okay. So let's quick do this calculation. So Newton's second law, we have the downward 1,000 and the upward 2,000. So 0, negative 1,000 plus 0, positive 2,000 plus the T in the positive X direction plus the V in the negative Y direction. And so here we get T is equal to 0 still. This time V is equal to positive 1,000 newtons. And now the moments about the Z-axis. Our about point is still going to be all the way at the left. The 1,000 doesn't produce 1. The 2,000 does. What's the moment arm of that 2,000? 0.5. Yep. Because this distance doesn't change depending on where this is. You see that? The distance between the left endpoint and that roller is fixed. Okay. So And that would be a counterclockwise moment. So we have positive 2,000 times 0.5. And then the only other ones are the m and the minus Vx is equal to 0. And so our function for m is 1,000x minus 1,000. And then the last one is for the x moment. So just add up the torques. That comes out the same as it did before. There was no torque, no additional torque happening at that roller. So we just have negative 500 plus fancy t is equal to 0. So fancy t is equal to 500 Newton meters. And so the first one we did, we got these functions that were valid for x between 0 and 0.5. This time we got these functions that are valid on the interval x between, what are the values here? 0.5 and 1. And all together, those make a piecewise function. So these give piecewise functions representing t, v, m, and fancy t along the entire beam. If you plot those as functions of x, you can, easily see where they're at maximums and minimums and stuff like that. See where you're concerned about this beam breaking, where you want to do some kind of stress analysis.